I would like to introduce the first speakers of the day. Jaroslav Trnka from UC Davis is going to talk about an introductory lecture on Amplituhedron. Thank you.
Okay, thank you very much. Thank you, Dan, Lauren, and Matteo. I'm sure it will be a great workshop. Thanks a lot for putting it together. So I was charged with giving a first introductory lecture on the Amplituhedron. So it will be mostly impressionistic. I will give some physics motivation to why this object, why we define this object, what it calculates, what is kind of the background of it. Then I will have few slides with the actual definition, more mathematical, and then also discussion of what are kind of open problems of that. But most of that is not technical, so I hope it will be accessible for everybody. And it's just to give a general idea. I'm sure that some of the later talks, which will be more specialized, will kind of give a proper definition and proper details of what the Amplituhedron is and what actually what are the calculations we would like to do. Okay, so let's first spend some time talking about the object that we would like to calculate from the physics point of view, which is called scattering amplitude. So there will be some of the physics background. So yeah, it's not necessary to understand all the details, but just to get some ideas for the mathematical part of the audience. So the scattering amplitude is a mathematical function that we use in physics to predict outcomes of experiments of scattering of elementary particles. So we scatter elementary particles at some large collider machines, and we would like to look more closely what happens, what are the outcomes of these experiments, and then deduce some physical laws from the results. And because of quantum, because of the quantum nature, the outcomes of these experiments are not given. They are only given probabilistically. There are many things which can happen, even if you scatter some fixed particles in the initial state. It's unclear what happens in the final states, and the only thing that you can calculate is probability. And this is given by an object in physics called cross-section. But the object that we really know how to calculate kind of directly from the quantum field theory, which is our framework for doing these calculations, is the scattering amplitude. Then we have to do some further manipulations with this object to get this physically interesting, relevant object. Now, what we are interested here for the purpose of the Amplituhedron, but also other developments in this field, is the scattering of gluons. These are certain types of elementary particles of strong interactions. At low energies, most of the matter is built from the hadrons, and at low energies, the gluons and quarks, the elementary particles, are trapped inside hadrons, but at high energies, if you accelerate them and then scatter, they are basically free. So we can really talk about the gluon scattering. And then there is a standard procedure in quantum field theory how to do these calculations, which was developed by Dirac in 30s and Feynman-Schwinger later in 50s. And this is first, you have to assume that the strength of this interaction is small, that the interaction is weak. And then you can use something called perturbation theory. So you can basically expand in some small parameter g, which we call coupling constant, and you get contributions which are weighted by higher and higher powers of this g. And the idea is that the higher corrections are subleading to the corrections which are only addressed with the lower power of g. And then Feynman developed this diagrammatic method how to do these calculations called Feynman diagrams. And therefore, the names of these amplitudes or these coefficients of the amplitude at given order is inherited from the type of Feynman diagrams that they contribute. So in the leading order is only Feynman diagrams which don't have any loops. We call them tree level. Then diagrams with 1 loop, 2 loops, and so on, higher loops. Unfortunately, this expansion is not convergent, it's asymptotic. So in case one wants to do resummation, there is necessary some further treatment of that. Now, as I said, our main object of interest are amplitudes of gluons in a theory called quantum chromodynamics. And this is a theory which describes these interactions like quarks and gluons. These calculations, these predictions of what happens if we scatter these particles are actually needed for uncovering new physics at these colliders, at the Large Hadron Collider in CERN, for example. And because it's necessary to have under control, to have very accurate prediction of what happens just in standard model, which is our model for particle interactions, elementary particles and forces, in order to see if there is some discrepancy and uncover some new physics. And in these calculations, the most complex part, the most complicated thing to calculate are exactly the amplitudes of gluons for many reasons. Yeah, there are also interactions with quarks, but these gluon amplitudes are really the main bottleneck for these calculations. And the standard procedure how to do it since basically birth of quantum chromodynamics in 1970s is to draw all the Feynman diagrams and follow the standard prescription and calculate the amplitudes, summing the Feynman diagrams, evaluate each of them using certain rules, Feynman rules, and then sum all of them, and then gives you the amplitude contribution in this expansion. Okay, so that's what people started to do. But this is very, as I said, these calculations are complicated, they are quite complex. If you do it just using the standard tools. And the prehistory of this subject dates to late 1970s, but when the most complicated process one can do is 5-point amplitudes, which means that you scatter 2 particles in the initial state and you get 3 different gluons in the final states at 3 levels, which means this is leading order in this perturbation theory. And if you just do it using the standard prescription, the result that you got are 24 pages of algebra like that, when these small dots are some variables that you associate with momenta and polarizations of these particles, some parameters of your scattering. So this is not very nice result, and you expect that it gets worse and worse if you go to higher and higher multiplicity, to more and more particles involved, or even going beyond this heating further, which was not possible back then. But these calculations were necessary because just from the practical perspective, in 1983, so a few years later, there was an approved construction of a new collider, it was called SSC, in Texas, which was supposed to reach very high energies in accelerating and colliding these particles. And therefore, there was a need for further theoretical predictions for higher amplitudes for theories to calculate in order to accurately predict what happens at these colliders and search for new physics. So the next amplitude on the list was a 6-point amplitude, so 2 gluons in the initial state and 4 gluons in the final state. So the construction of this collider was terminated in the early 1990s, but the calculation of this amplitude was actually done a few years after 1983, 1984, then later in 1985. And this is what is now called Park-Taylor formula. If you just do straight the calculation, it involves calculating 220 Feynman diagrams and roughly 100 of pages of algebra of what I showed before. This is the result for this collision, for this amplitude. And these 2 people finished that calculation in 1984. They wrote a short paper, 40-page paper, which basically only contains the result itself, written in some special notation, using some basis of some terms with a lot of coefficients, matrices, and so on, in order to efficiently package the result in the paper format. And in the end of the paper, in the conclusion, they also write that furthermore, we hope to obtain a simple analytic form of the answer, making our result not only experimentalist, but also theorist delight. So this was a result for experimentalists to put it in their computers back in the 1980s to predict these processes, but they also hope to learn something from the structure of the result. And indeed, within a year, they realized that these 100 pages of algebra can be rewritten into a single line formula. So this was kind of a first evidence that there is something special about these scattering amplitudes, which is invisible in the standard methods of Feynman diagrams, and there are huge simplifications. Okay, and this is the Park-Taylor formula written in terms of momenta, but nowadays, this is for a square of the amplitude. Nowadays, we write it in terms of other variables, so you might have seen this formula written in a different form, but the structure is the same. Okay, so starting from there, people develop new methods how to calculate amplitude, but they are still built on something that we learned from the Feynman diagrams, and this is doing the perturbation theory. That it's important to look at the amplitudes order by order in this perturbation theory. Look at these 3 amplitudes, which consist only of 3 graphs, 1 loop amplitudes, 2 loop amplitudes, and so on. And because at each order of perturbation theory, we can apply some strong constraints of what is the structure of the result. And these constraints are also related to an old idea which predated this QCD, the quantum chromodynamics, called analytic S-matrix program from 1960s, when people tried to calculate the amplitude directly, pose it as a mathematical question: what is the function which satisfies a set of conditions that we can uniquely fix that function? And this program was not successful because it was just too complicated, too difficult. You couldn't find enough conditions to fix the amplitude directly. However, the idea of fixing the result from certain constraints that the physics imposes, or later also reformulated in some mathematical way, this is a leading kind of idea which also led to further progress, but applied in the context of perturbation theory. So doing it for the full amplitude, resumming everything because it's just too complicated. Okay, so these modern methods kind of originate from the unification of both of these ideas, and there are many different ones, starting from generalized unitarity in 1990s, recursion relations, and many. So now it's a very rich field with many different approaches, also from string theory and from other subjects. Now, let me just give some small hints of what these new methods bring and how they simplify the answer. So I will be a little bit jumping here ahead, but for these 3-level amplitudes, so the ones that Park-Taylor did, and then later was done for more and more, when in terms of Feynman diagrams, they only contain 3 graphs with no loops. Jaroslav Trnka and Witten in 2005 formulated recursion relations, which means that once you calculate the amplitude for some fixed multiplicity, let's say for six particles involved, 6-point amplitude, in order to go farther to 7-point, you should do some recursion. You shouldn't calculate everything from scratch, but you should recycle the information that you already obtained in previous steps. And these recursion relations happen to be extremely efficient. And you can see here the comparison between the number of Feynman diagrams and the number of terms in this recursion. And this is for kind of general case. Yeah, this Park-Taylor version, and here was only 1 term for the 2 to 4 for the 6-point scattering. This was kind of for a one special so-called helicity configuration. But in the general case, it's slightly more complicated. So these recursion relations are extremely efficient, formulated by BC and W in 2005, and using some more modern methods related to on-shell diagrams and positive Grassmannian, which I will talk about later. You can even kind of, it's the same calculation as done here, but you can basically label the graphs. The information that is necessary to build the answer is extremely minimal. Yeah, basically everything boils down to the set of some permutations of labels, and that's the invariant way how to basically classify the terms that you need to sum in order to get the amplitude. Yeah. So the amount of kind of irreducible data in the amplitude is extremely small, and the Feynman diagrams just artificially make it complicated. But there is certain reason why they do it. So it's for certain questions, it's actually good to have this method in hands. But for the calculations of these amplitudes, there are much more efficient methods. Now, this was about trees. I want to mention a little bit about these loop amplitudes. So the next order in this perturbation theory, when the amplitudes contain internal loops. And these are more complicated. So these three amplitudes are only rational functions of our parameters of kinematics that we describe elementary particles. But these loop amplitudes are more complicated because they involve loop momenta, so some unspecified parameters that we need to integrate over. And despite they start as rational functions when we do the Feynman diagrams, for example, or some other methods, generalized unitarity, then they need to be integrated over some parameters, and these integrals are typically divergent. We have to treat the divergences in a certain way. And even after doing that, the type of functions that we get are complicated. They are transcendental functions, polylogarithms, elliptic functions, and worse. So this is a very kind of very open field with a lot of open questions, a lot of work being done on doing these loop integrals and these loop calculations, because they are needed in physics, yeah, when you want to calculate these amplitudes. Yeah, one method I would like to mention here are unitarity methods, which is basically the first big discoveries done in this field in the early 1990s. And this is a reorganization of the Feynman diagram expansion when you basically at the level of this rational function called integrand, which will be also important for us when we talk about the amplituhedron. This will be done for this integrand, not for this function, not for the amplitude. Yeah, that function is too complicated, but for the integrand, you can also conveniently expand it in some basis of terms and then calculate its coefficients. And despite this looks kind of a minor thing, this is extremely important for the efficiency of that. Okay, so now to make further kind of progress, we will kind of limit our scope in what we will be interested in. So in the beginning, I motivated the thing with scattering of gluons and quantum chromodynamics, but the amplitudes in this theory are more complicated, especially at loops, and they have certain features that we don't know how to address at the moment using some of these more modern methods, but we will hear something about NEMA tomorrow, about Young-Mills theory, which is a cousin of this QCD. But a lot of the progress in this field has been done for a special version of the theory of gluons called planar n=4 super Young-Mills theory. So it's starting with this theory of gluons, but adding supersymmetry and actually maximal number of supersymmetry. And also the number of colors of each gluon, there is some parameter, and C, the number of colors, goes to infinity, which simplifies the calculations, because then the only kind of contributions that we can get, even at the Feynman diagram level, here are diagrams which are planar. So this diagram, yes, and this one, no. That will not contribute in this planar limit. Okay, and yeah, and there are also some interesting connections via ADS-CFT correspondence to supergravity, and we can also learn a lot from there. Now, the thing that we lose by basically going to this toy model for the interaction of gluons, but it's a valid theory, of course. It's that now we will not deal with one kind of divergences, which are called UV divergences. They are completely absent in this theory. And we will also not have this feature that if we go to low energies, that's the gluons and quarks start to be trapped inside hadrons. So there will be not such a thing. Yeah, so this is called confinement. There is nothing like confinement here. Now, why is it a good toy model then? Well, one indication is that at this leading order, at 3 level, the amplitudes of gluons in this theory are the same as in this quantum group dynamics, as the theory of gluons in the real world. And if we go to these higher orders to loop amplitudes, these loop amplitudes are simpler. The perturbative series is no longer asymptotic, but actually convergent in this planar limit. So if we can get a handle over the whole perturbation theory, we can hope about resumming things. But still, despite the loop amplitudes are simpler, there are some similar features, at least for the part of the loop amplitudes in QCD. So there is definitely something to learn here. And there is a past experience with Young calculations in this theory that the new computational methods were basically, in many cases, first developed here and then extended to other models. So this is a good toy model. But despite some huge simplifications in calculating these amplitudes, in some cases, due to a large number of symmetries of the theory, the results are simpler. Still, going higher and higher orders in this perturbation theory, we just get more and more terms. However we package the result, however smart and convenient we use the framework in which we calculate the amplitudes, eventually the number of terms will grow. Yeah, so we would like to get some understanding of all amplitudes, but from this point of view, writing the diagrams, either Feynman diagrams or diagrams in these unitarity methods, they will eventually grow, and yeah, of course, for infinite number of loops, they approach infinity. Yeah, there is no kind of cap on the complexity of things that we can get, even if we write them in the most compressed and most convenient way. Okay, I will, so this is still a story about the integrand, and this is where the amplituhedron will eventually live. But I would like to mention a few other things before actually going into the amplituhedron, and these are some other methods in amplitudes which kind of skip this step of first calculating the integrand and then integrating and doing some treatments on that and get the final answer for the amplitude. And one of them is called symbols. And the idea is that we would like to skip the integrand step completely. We would like to directly go to the function space on the right-hand side here, left-hand side here, and construct the amplitude directly there without constructing the integrand and then integrating. And it happens to be that there is a very convenient reduction of information of these functions of many variables, because they have to parameterize the momenta into some code called symbol, which encodes the branch cut structure of the amplitude. So it's not the function directly, but it encodes the branch cut structures. It's a code which involves some entries, and these entries are filled by something called symbol letters, which tell you where the branch cuts are and what type of branch cuts these are. And the usefulness of this approach became obvious in 2009 when these three people, Del Duca, Duran, and Smirnov, calculated certain amplitude, two-loop 6-point amplitude in this theory. And similar to what happened with Park-Taylor factor, when they finished the calculation, they got 30 pages of result. In this case, it was not rational functions, but something called some polylogarithms, Goncharov polylog, harmonic polylogs, yeah, various functions of many variables. And it didn't look that it would simplify to anything nice or anything simple, but when extracting the information, the invariant information from this answer, because these functions satisfy a lot of identities. They can be written in many different ways. So this is not a unique way how to write anything. And it's not clear which identities to use to potentially simplify it. Using the symbol method, you can once you calculate the symbol of this function, you can reduce everything again to something like two-line formula. This is the symbol, and then you can upgrade the symbol back to the function space, which looks like that. And the symbol for these 30 pages is these 2 lines, and it's equal to that. So in principle, there is some long sequence of identities between these functions, which turn these 30 pages into 1 line. But it's very hard to see. Yeah, but the symbol is a tool how to do it. Yeah, so the symbol contains invariant information about the branch structure of the function, and then we can decide exactly how do we want to realize it in terms of functions. The symbol doesn't contain all information. Of course, it misses things like constants, which don't have any branch cuts, but for that we have to use extra information to fix them. And there is so this discovery of symbols was done by Mark, Anastasia, Goncharov, and Vergu in 2009. And the idea of symbols was then used heavily by Lance Dixon and his collaborators to run the hexagon bootstrap, which is the effort to calculate 6-point amplitudes in this theory to very high loop order. And they were able to get to extremely high, kind of unbelievable loop order, 8 loops, but also they have some all loop order conjectures for various things. Okay, so after this kind of introductions, a little bit broader, we get also to our picture, which is not the picture for the amplitude, the final amplitude itself. It's a picture for the loop integrand. So for the 3-level amplitudes, they are rational functions, and loop integrands, which are also rational functions. And so this is the amplituhedron conjecture, which is saying that this function that you normally obtain using Feynman diagrams or these recursion relations, unitarity methods, these rational functions can be also calculated as a certain volume, or more precisely, some differential form with logarithmic singularities on the boundaries of the space. I will get back to it later. On some space, this amplituhedron space, which is defined by some certain set of conditions, and these conditions involve variables which parameterize the kinematics of gluons. So you start with these gluons with the particular scattering process. It's parameterized by some parameters, and these parameters go into the definition of the geometry. Yeah. So while there are no gluons, no kind of lines of particles here in this picture, the kinematics is hidden in the locations of these vertices and in the way how they are grouped together with these spaces. And now the different ways to express the amplitude corresponds to different ways how to triangulate this object into smaller pieces, when each kind of piece in the triangulation would correspond to some building block, either Feynman diagram or a term in the recursion relation, or so on. And apart from kind of purely mathematical and computational advantage of what we will see in some cases later, it's a very different kind of way to think about particle scattering to anything which was done before, because, as I said, there are no particles here. Really. There is no dynamics going on. There is nothing which tells us how the particles interact in this picture. Yeah, everything is reduced to some static geometry. From the other point of view, this also, at the moment, it is hard to see some general framework how to extend it to arbitrary theory. There was some progress on that recently, how for some Lagrangian, how to associate certain geometry. But at least at this level, there is no dictionary how to go from this theory to this geometry. Yeah, so it's more like you have to find the geometry, to guess it, and check that it calculates the same amplitudes as the Lagrangian. The Lagrangian is very general. You can do it for any particle content the standard methods work very generally, but as we saw on this Park-Taylor example and other examples, they don't provide the most efficient way how to calculate these things. And they also don't provide kind of a definition to what the amplitude is. The amplitude in the standard picture is a sum of terms that you generate using some rules. While in this picture, there is kind of a definition of what the amplitude is the volume or some canonical differential form of some geometry that you define. And the Amplituhedron is one example of a larger class of positive geometries. So I think we will hear more about it later. So I will not go more deeper into it, but now there are more examples of positive geometries which show up in the context of scattering amplitudes. Of course, there are definitely more of the ones which don't show up in the scattering amplitudes yet. But Amplituhedron is one example of them. So still, it's actually a conjecture that the Amplituhedron is a positive geometry based on the definition of what the positive geometry is. You will hear in the next lecture. Okay. So on the path to the Amplituhedron, I would like to start with discussing on-shell diagrams and plate diagrams, which played an important role in the development of this. And the main object of interest here is a Grassmannian GKN, so configuration of k-planes in n dimensions, which we can represent by a matrix, k by a matrix modulo GLK. Now, the positive Grassmannian, G plus Kn, or totally negative Grassmannian, corresponds to this space with a restriction that all ordered minors, main minors, k by k minors, are non-negative, so cannot be negative, 0 or positive. And the boundaries of this space corresponds to the minors, consecutive minors being sent to 0. If you take the columns which are consecutive and send them to 0. So this space happens to play a very important role in scattering amplitudes and the Amplituhedron in particular. Now, we can look at the cell on a particular subspace in this positive Grassmannian, which is given by a list of vanishing minors. So for our purpose, it's actually convenient if we take this k by n matrix, think about it as k-plane in n dimensions. We can represent it like this, but also like this as a collection of rows or collection of columns. And this collection of columns, this is n columns, which are a component. This is a convenient way for us how to visualize what the space is, because we can think about it as endpoints in k-dimensional space, in our case, projective space. So the positive Grassmannian G plus 2n, this is 2 by n matrix, corresponds to endpoints on a line. And the positivity, the fact that these minors were positive, correspond to convexity, or here ordering, canonical ordering of these points. For G plus 3n, for the next space, we get an convex n-gon in plane, projective plane P. So these two configurations would correspond to the top cells of the positive Grassmannian G plus 2n, G plus 3n. 6 and it's 6 in these examples. And this way of thinking about these positive Grassmannians makes it nice to see the boundary configurations. So for example, for this G plus 3-6 space, we start with 6 points in a plane in the convex configuration. And then going to the boundary corresponds to sending some minors to 0, the consecutive minors to 0, which moves some points to special configurations. So for example, 4, 5, 6 is 0, sends 4, 5, 6 to be on a line. And then we can further specialize the configuration. So starting from the top cell, we can access lower dimensional cells in this space by moving these points to special locations, merging the points as well, or removing the points corresponding to sending the given column to 0. Now, if we take one of these configurations and we can build the matrix back by parameterizing the points here. Yeah, we basically have to just capture all the linear dependencies between these vectors. Here, the C vectors. But if we just parameterize it in a random way, we get some matrix which corresponds to this configuration, but it wouldn't make manifest that the matrix has all minors, the main minors, in this case 3 by 3 minors positive. So the question is, can we find parameterization which makes that manifest? Yeah, where you can send the parameters being positive, and then in this matrix, all the main minors will be positive, and that would actually correspond to the cell in the positive Grassmannian. And the way how to do it was found by Postnikov, and this is using so-called play-big graphs. So play-big graphs are graphs which consist of two trivalent vertices, blue or black and white, and the graph represents a cell in this positive Grassmannian, and using certain procedure of with associating variables with the edges of the graph, we can then fill the entries of the matrix in a way when the parameters being positive corresponds to the matrix being a positive Grassmannian, having all the main minors being positive. And yeah, and there is some procedure how to do it that Postnikov gave using so-called perfect orientation. The variables that we associate with the edges are called edge variables, and there is a prescription how to calculate the entries of the matrix. Okay, so the cells in this positive Grassmannian correspond to these play-big graphs, and some special set of play-big graphs called reduced play-big graphs are only labeled by permutations of n labels. So this is what I said before, when we do these recursion relations, we can only basically specify certain permutations, and that gives us all information about the amplitude in the language of these play-big graphs, which happen to play a role in physics. These are these permutations which are associated with this special set of play-big graphs. And now going to a boundary of this cell in positive Grassmannian, which, for example, corresponds to merging points in this configuration, imposing some linear dependency between points, corresponds to sending one of these variables that we associated here, the edge variables, with the edge to 0, which removes the edge in the graph and gives us some simpler play-big graph. So there is a nice correspondence between going to the boundaries of the space on one side of this positive Grassmannian and between operations on these play-big graphs on the other side. Okay, and then so this was purely on the math side. The connection to physics is that these graphs also play a role in physics. They correspond to something called leading singularities. They are building blocks which can be used to calculate amplitudes using these recursion relations. So they are alternatives to Feynman diagrams. Yeah. While in physics, these vertices corresponds to some amplitudes that we glue together. In the context of play-big graphs, yeah, they are just vertices of these play-big graphs, which we built for each cell of this positive Grassmannian. But then there is a connection between these two worlds. It's not that they just use the same graphs for different reasons, one for some amplitudes calculations and one for the characterization of this positive Grassmannian. But there is a way how to do the physics calculation using information from the positive Grassmannian. Okay, so once you build your C matrix here using this prescription, then you can define a differential form, some simple differential form on this space, and with extra delta functions, which we'll discuss just in a second, you can turn the parameters of the Grassmannian and the H variables in this matrix into kinematics, into some parameters which represent the momenta of particles, and then evaluating this function, this integral, and there is actually no integral to be done, everything is evaluated on residues, turns into the kinematical functions that we care about in physics, which calculates the amplitude using these recursion relations. And just to line up parameters on both sides, the Grassmannian is G plus Kn. The cell is G plus Kn, has two parameters K and N. N corresponds to the number of these external legs, and K is some factor that you can calculate from the graph, but it corresponds to the number of rows of this GKN matrix. And in physics, N is the number of external particles that we scatter in the process, and K corresponds to something called helicity. Helicity number corresponds to how many of these gluons are minus gluons, negative helicity, and how many of them are positive helicity. So we have two types of gluons that we scatter. Okay, so what is the more precise connection here? So the differential form that we would like to define on this cell in the positive Grassmannian, represented by the graph, is a form with logarithmic singularities on the boundaries. So this means that we have some differential form. Whenever we go to close to the boundary x is 0, we would like to develop a factor dx over x. So the singularity should be logarithmic. And on the cell, this form on the cell in the positive Grassmannian can be written in two equivalent ways. One is using these H variables, which are these parameters on the plane graphs. And it's just a wedge product of all d alpha over alpha for all these variables. You can also rewrite it in a way which is not fixing, because this is some fixing of the gauge of the C matrix using certain H variables. You can also write it in some unfixed way when you kind of unparameterize the parameterization that you did for the positive Grassmannian. Okay, so this way makes manifest that all the singularities are logarithmic, but depends on parameterization. This makes manifest what are all the boundaries of the geometry, because they show up as poles in this form. Okay, so this is the part about this form. So this d omega is just this simple thing, yeah, the one which shows up in this connection between the plane graphs and physics. Now, what about these delta functions? So these delta functions turn these alpha parameters, these H variables, or any other variables you use, into kinematics. And these delta functions, we integrate over them. So it's basically we just evaluate the alphas on the arguments of these delta functions. And these delta functions is actually a very nice way how to introduce the Grassmannians into physics in the first place, even without knowing anything about plane graphs or geodiagrams, nothing. And the idea is is just thinking about the kinematical variables we have in physics. So the information about the energies and momenta of these particles are traditionally given by something called 4 momenta. So it's a 4 vector in 4 dimensions, in the number of dimensions we live in, 3 plus 1. And we can represent the 4 momentum. We can write it in a matrix, in a 2 by 2 matrix. And in order the particle to be massless, because the gluons don't have any mass, the determinant of this matrix must be 0 in order to describe a massless particle. So we can then write it as a product, as instead of matrix, we can rewrite it as a collection of 2 vectors. And because if we write it in this way, obviously the determinant will be 0. And we call them lambda and lambda tilde. So instead of 4 momentum P, we have 2 spinors, lambda and lambda tilde for each particle. And then we can package all these spinors into 2 by n metrics. So these are lambda spinors, and lambda tilde spinors are also 2 by n metrics. And then we have a condition on these 4 momenta. They have to sum into 0 because the energy must be conserved, the momentum must be conserved in this scattering process, which means that these lambda and lambda tilde, now thought about as 2 planes, must be orthogonal to each other. So then, therefore, we can write it as this delta function lambda dot lambda tilde inside a delta function. This must be 0. It must be orthogonal. And now introducing Grassmannian is natural when we want to linearize this quadratic condition on lambda lambda tilde, bilinear condition. We would like to write it as 2 separate conditions on lambda and lambda tilde separately. And the way how to do it geometrically is not saying that lambda and lambda tilde are orthogonal to each other, but saying that lambda is contained in some k-plane C, and this C plane is orthogonal to lambda tilde. So we kind of decouple these conditions together. And these are exactly these 2 delta functions that we have here, which make realize this condition. Lambda is contained in C, and lambda tilde is orthogonal to C. So as a consequence, lambda and lambda tilde are orthogonal to each other. Now the C plane is not fixed by this condition. Yeah, it's a K-plane, and there are many K-planes which involve a given 2 plane are orthogonal to other 2 planes. Okay, so these delta functions which show up here are the ones which exactly show up here. So the parameters of this C matrix from this delta function can be then solved in terms of these lambda lambda tilde. Yeah, so that's the idea. And once you kind of count the number of variables that you have in the C matrix and the number of parameters that these on-shell diagrams / plate graphs have, which are relevant for physics, that it exactly matches, and you just solve for all variables. And the thing that you get in the end is just depends on lambda lambda tilde and nothing else. Okay, so we started with this simple form, the D-log form, for the parameters of the C matrix, which are realized in these plate graphs. And then in the end, we got a function of lambda lambda tilde, which parameterize our kinematics of the scattering process. And this is the thing that we can also calculate directly from amplitudes, but we also get it here from this connection. Okay. So these on-shell diagrams show up in physics, but we can use these positive Grassmannian tools to calculate them. And then once we go to Amplituhedron, we will have to change the variables again from lambda lambda tilde from these variables to something called momentum twisters, because then it very naturally well lived. But there is also a version of the Amplituhedron which uses directly these spinor helicity variables called momentum amplituhedron. Okay, so now let's go farther. So this is about the connection to Grassmannian and about new building blocks for amplitudes, which are these on-shell diagrams / plate graphs, which also play a role in mathematics. Now, what about the idea that amplitude is a volume, or then you will see that it's a differential form on this amplituhedron. And that actually goes back before all of that showed up in physics. And this goes back to the idea of Andrew Hodges, who studied certain recursion relations in momentum twister space. So what are momentum twisters? They are another new variables, which purpose is to trivialize this momentum conservation. Yeah. So we said that the sum of all momenta is 0. It corresponds to these conditions of lambda lambda tilde. But let's introduce another variables where we don't have to worry about it. Yeah. Once we have these new variables, Z variables, momentum twisters, then for any choice of these momentum twisters, if we go back to momenta, they correspond to momenta which satisfy momentum conservation. Okay. So there is a way how to repackage the information from momenta into momentum twisters you can forget all that and just think about it as points in projective space P3. So for each particle, we associate momentum vector Z, which is points in P3. But in order to define it, we need an ordering. We have to order the particles. Okay, and this is exactly where the ordering enters, because in this theory we are interested in for gluons, indeed the particles are ordered 1 to n. Yeah, so we can use these momentum vectors. So Hodges used these momentum vectors and studied from physics point of view these recursion relations, which we now also know can be realized in this on-shell diagram language, but he didn't know that back then. And he wrote explicit formulas for that. And the thing that he wanted to see is one feature, because in the recursion relations, there are certain spurious poles in the denominator. So this is, we would start with some formula in terms of this lambda lambda tilde. If we go to momentum vectors, we get these types of formulas when these 4 brackets corresponds to 4×4 determinants of the momentum vectors for the labels that you can see in the brackets. Yeah, so this is a change of variables. So he wrote these formulas for the 2 terms which contribute to one special amplitude. He calculated with 6 gluons at 3 levels. Some of them are positive, some of them negative. And he realized that these formulas also corresponds to volumes of tetrahedra in momentum space. That the same formulas he got from his recursion relations also give volumes of tetrahedra. When each face of the tetrahedron is labeled by one of these 4 brackets. Yeah. And the interior face corresponds, it's a spurious face. Once you glue them together, it disappears. And it corresponds to a spurious pole in these expressions that he calculated. So there is one term which is shared between 2 of them, and it's exactly in the geometric picture corresponds to this internal phase which cancels. So these two, this recursion relation formula is then interpreted as a particular triangulation of the polyhedron in terms of 2 tetrahedra, and the amplitude is a volume of this polyhedron. Yeah, so this was the first time I'm thinking about the amplitude as a volume and as a single object. So after that, there was kind of a weak conjecture that amplitude should be some volumes of some regions in some space. But then later, because of the connection to the positive Grassmannian, it kind of became obvious that the space in which this Hodges idea generalized must be positive Grassmannian. And also the volume was then replaced by the notion of this D-log form that we already discussed before. Okay, so 7 minutes. Okay, so let me quickly give some how to go farther and how to eventually run into the amplituhedron. So everything starts with thinking about polygon in a plane and interior of the polygon. But let's start only just with triangle. So we start with triangle in a plane, 3 points, and we would like to describe the interior of that. So there is point Y inside this triangle. So we can write Y as a linear combination of these points Z1, Z2, Z3. These are points in a projective plane P2. And if we take a linear combination with coefficients being positive, that the point Y is inside. We can access boundaries by sending one of these parameters to 0 and go on the line 1, 2, 1, 3, or 2, 3. Or we can go to the second boundary when we send 2 of the parameters to 0 and localize Y directly in a vertex. Now, we can also use a parametrization, because this is in projective space. We can send one of the C's to 1, and then the boundaries are also located at not only at 0, C2 and C3, but also at infinite. Now, if you want to write a logarithmic D-log form, so a form with logarithmic singularities of the boundaries, that it blows up the form as dx over x whenever we approach the boundary, Then this form in this parametrization is just this simple form, dC2 over C2, dC3 over C3. But we can unfix this parametrization and write it in this way, where these three brackets are now 3×3 determinants made of these z's at this point 1. So, and this is projective in all variables. So this is a D-log form on a triangle in a plane. Now, if we go to a polygon, we would like a convex polygon. So we have to impose a conditions on these z's to form a convex polygon. And this condition is that if you write these z's into 3×n matrix now, all the ordered 3×3 minors must be positive. So if this is true, then the z's form a convex configuration. If we put a point y inside that convex polygon, we again write this linear combination of all points. And if the c's are all positive, then we are inside that polygon. So we can formally write it as y equals c dot c, where c is a positive Grassmannian now, g plus 1n, it's just a row of positive numbers. And z is some 3×n matrix, which is positive also, because all the 3×3 main minors are positive. We don't call it Grassmannian because we are fixing z's, we are not moving with them, so we just call it a matrix M. Okay, now what is the form on this space with logarithmic singularities on the boundary? So the first guess is that it might be something like this, which is wrong because this is still a two-dimensional picture and this is an N form. So actually in some parametrization, it's a more complicated two form. Yeah, it has a lot of factors in the denominator and factors in the denominator corresponding to boundaries, and there's some numerator factor as well. How to write this form? Well, the easiest way is to triangulate. So we cut the polygon into a collection of triangles. For each triangle, we can write this D-log form, which is just a two form. But the problem of doing it like that is that in each triangle has its own variables. Yeah, in one it's C2, C3, then C5, C6, and so on. So if we want to sum them together, we first have to unfix and write it in this projective form using these y variables and the 3×3 minors involving z's and y's. Once we do it, we can just sum them together. And this is a form with logarithmic singularities on the boundaries of the whole polygon. Now, the boundaries of the polygon are just lines I plus 1, lines connecting adjacent points. But if we write a form like that, it will contain spurious poles, yeah, like 1, 3 or 1, 4, yeah, because these are they come from this internal, from this triangulation. Yeah, the two of the triangles have this pole, but once you sum it, the pole goes away. So these are spurious poles, and they must cancel in the sum. So there also is a form. Once we sum these two expressions together, it has only 6 poles, but it has some non-trivial numerator. How to find a form in this case is actually possible, going directly here, but how to do it in general case beyond that is an open question. Yeah, you typically know for more complicated cases how to do the triangulation, at least in some, but you don't know how to write a form in this way, which doesn't have these spurious poles. So in this case of polygon, you can actually write a numerator and completely fix the numerator by canceling all spurious singularities. So now that it has 6 poles corresponding to 6 edges of the polygon, but it generates a codimension 2 singularities at points which are not vertices of the polygon. So for example, if you take a line 1, 6 and 4, 5, they intersect outside the space at this point, and the denominator would generate a singularity there. So the numerator must vanish in order to kill that singularity. So this actually fixes the numerator completely. Now, once we have this form for this polygon, we can actually extract from it something, in this case, called like quasi-amplitude or a toy amplitude. This actually doesn't correspond to any real scattering, but the main idea of the amplituhedron is already here. Yeah, so we have this polygon, we get a differential form. So this is just for triangle here, and we extract some function which would calculate some scattering process. if you repeat the exercise, not in P2, but P4, so we go 2-dimensional higher, so we have a simplex and eventually glue it into higher polyhedron, and we do exactly the same thing. The function that we get from physics, from the d-log form on the simplex or the polyhedron, would be actually already relevant for some scattering. Yeah, this would be called R invariant, and this is building block for NMHV amplitude, yeah, for K+1 amplitude. And going 2-dimensional higher also changes the boundary structure. So instead of lines II+1 in the polygon, it is now 3 planes II+1, JJ+1. So they have, yeah, it's a 3-dimensional boundary, and it has 4 vertices, II+1, JJ+1. Okay, so we are already almost at the amplituhedron. So now writing it more formally, what is polygon? So polygon is an interior of the polygon, is a collection of all points y, which you can write as C dot Z. C is a positive Grassmannian G+1n. Z is some fixed matrix of Z's, which are convex, which means that all the 3x3 minors of these Z's are positive. And the Y then lives in G13. Yeah, this kind of in this contraction, the one cancels, so it's G13. It's not a positive Grassmannian G13, it's just G13, which in this case is just P2. Yeah, so this is polygon. Alternatively, we can also give in this projection, so you can think about it as a projection from G plus to N, from these C's to G13. We can also alternatively think about it as a collection of 2-dimensional cells. This is n-1 dimension, it has n-1 independent parameters. Modulo 1, you can always fix one of them to 1. But you can also give a triangulation here, which is saying that we only take the triangles. The triangles are 2-dimensional cells in G+1n. Yeah, they have only 2 non-zero values exactly, and 3 non-zero, one of them fixed to 1, and 2, 3 parameters corresponding to vertices of that triangle. So giving this collection, you can also run this map, and you basically map triangle by triangle that they glue together in the polygon. So you can get a polygon by mapping the whole G+1n, the n-1 dimensional space, or a collection of 2-dimensional cells. But this will be already a triangulation. Now, the 3-amplituhedron is just direct generalization of this idea. Just change some labels. So instead of G+1n, a collection of positive numbers, these C's, you have a top cell of positive Grassmannian, G plus Kn. So it's K by N matrix with all K by K minors being positive, and also the dimensionality of Z's grows. So instead of 3-dimensional Z's, they are upgraded to K plus M dimensional, where M is some parameter, which is in principle 3 in mathematics. In physics, you like to set it to 4. Yeah. So, and then the C dot Z is a map from G plus Kn to some space. If you cancel these labels, it's G, K plus N. Okay. So, and we can think about that then as a configuration of K-planes in some projective space P, K plus N minus. If you look at the labels, this is what you get. Okay, and the d-log form on this space, analog to what we kind of had here, or the sum of those, already is giving you all 3-level amplitudes of gluons on this here. And the K parameter here kind of labels which helicity center of amplitudes you get. So this is, you see that there is only one small step from the polygon over here by just changing 1, label 1, and 3 K and K plus N. Yeah. Otherwise, the definition stays the same. Of course, this page is much more complicated than polygon. Yeah, but I just wanted to emphasize that the definition is a direct generalization of polygons. You replace the row of positive numbers by a positive Grassmannian, and that gives the 3-level amplituhedron. Now, so this calculates 3-level amplitudes. The loop amplituhedron, calculating these loop integrands, has more structure. So in addition to this C matrix, the positive Grassmannian G plus Kn, You also have a collection of D matrices, and the D matrix is a line, so it's a 2 by n matrix defining a line. Each line corresponds to one corresponds to one loop momentum. So you have L of them if you go to L loops. And then, yeah, you have some positivity conditions between this. The C matrix is a positive Grassmannian, and the C together with any number of these D's must be also a positive Grassmannian. Okay, so there is a generalization of that. This space is not completely kind of understood even before that, but this is the definition. And this gives the integrand, so going from tree to loop. So the other amplitudes object, we are interested in the integrand of amplitudes in this theory. I would like to also mention that there is an alternative way how to talk about the amplituhedron, not as a projection of the positive Grassmannian, but the definition that we gave with Hugh Thomas and Nima, when and it was motivated by a question, how to decide if point Y is inside or outside the space. Yeah, note that in this projection, this is almost impossible to decide. Yeah, because you would have to prove that the point Y can or cannot be written as C dot Z. Yeah, if it can be, then it's obviously inside. But how do you prove that it cannot be? Yeah, that's almost it. That seems impossible to prove. Yeah, so we gave the definition which uses just inequalities. So there is a set of inequalities. If you choose point Y and it satisfies inequalities, it's inside. If it doesn't, then it's outside. And these inequalities corresponds to inequalities corresponding to boundaries. So you have to be kind of on the right side of the boundaries, like chopping the space, something familiar from the polyhedron. But this is not a polyhedron. Amplituhedron is not a polytope. Polyhedron or even polytope. So there are additional inequalities which are not boundaries, and these are called sign flips. So there must be certain amount of sign flips and some sequences of the brackets made from this Y and the Z's. Yeah, so there are additional data. If you satisfy it, then you are inside. Okay, so let me just kind of outline what is the, so we have the definition of the space. We define this logarithmic form with logarithmic singularities. We can extract an amplitude from that. Now, the main technical challenge is to calculate the form. Yeah, the definition we already have. The only way how we know consistently how to calculate the form, but it has kind of limits of how to do it, is to triangulate. So if we know how to triangulate efficiently these spaces, or maybe all of them, we would be able to calculate the amplitudes to all cases. But we don't know how to do these triangulations. It seems like a hard problem. Yeah, but the physics problem of calculating amplitudes is reduced to a problem of triangulating the amplitude. Once you know how to do it, then the rest is easy. Yeah, and yeah, so these are just a few words how different it is from physics. So let me here end with showing one particular problem. What does it mean to triangulate, or what is the thing that we would like to do, and what seems like impossibly hard from the physics point of view. From the math point of view, you can define the problem, and maybe it's still impossibly hard to solve it, but at least it's formulated in a way which might be solvable. Yeah, and this is a 4-point problem. So this is reducing the number of these external legs to minimum, which is 4. For 3, it's already too simple. Yeah, you kind of get 1. Yeah, nothing interesting. But for 4 external legs, this is the minimum number of external legs you can have. But you go to infinite loop order. So you kind of want to calculate all of these 4-point amplitudes. So the geometry is very simple. It's a geometry of L lines. L stands for this loop order in P3. And these L lines, AB, yeah, you have some Z1, Z2, Z3, and Z4, which form just a simplex here. And you would like to find a configurations of all these lines AB. And the amplituhedron gives you the constraints on these AB lines. So written in terms of convenient parameters, the point A and B as a linear combinations of these z's. You can write it in 2×4 matrix. This is actually a positive Grassmannian G plus 2, 4. And in some convenient parametrization, it just means that all the parameters of this AB line are positive. So this is very simple space. If x, y, z, w is positive, run from 0 to infinity. It has trivial D-log form. Everything is great. But now if you have L lines, they're not only each of them is parameterized by 4 parameters, x, y, z, w, they are all positive, but in addition, they satisfy some quadratic inequalities. Yeah, so this inequality between any pairs of the lines j and k, then this difference between x parameters, z parameters, and then y and w, they must form this inequality. So this is the definition of the space. You can write it on one line. This is the space. It's 4L dimensional space. And you would like to triangulate the space. Once you triangulate it, which means that for each parameter, you can write the x or y, z, w, any of these parameters, the minimal value and the maximal value. So you turn it into a line segment. Then you can in easy way write a D-log form for each of these parameters. But then this is the hard problem. Yeah, how to do it. Okay, you can reformulate the problem as some vectors in the positive quadrant. Red vectors, blue vectors, when these inequalities turn into this scalar products between the difference of all pairs of red vectors and blue vectors. Okay, there is a new attempt how to solve the problem recently using something called negative geometry. So Shruti will talk more about it in her talk. Okay, so this is my one slide summary. So the Amplituhedron is a new mathematical formulation of scattering problem of gluons in this certain quantum field theory is planar for super young males for the 3-level amplitudes and loop integrands. I said in the beginning there is this whole field of calculating the actual amplitudes, these transcendental complicated functions. We are not doing it here. Amplituhedron is believed to be an example of a larger class of positive geometries, and Thomas will talk about positive geometries more generally. Provides a promising tool how to do higher order and maybe even all loop order calculations because it defines the problem. And then the question is just how we approach the problem. In the standard physics point of view, the problem is not well defined this way. And there will be talks on that as well this week. And it's also a great playground of new mathematical ideas in explorations, which hopefully will also find connection to physics in the future. There will be a number of talks for that as well. Okay, thank you very much.